Hey, welcome to Analog Output. And yeah, it's been a long time since I posted a video. Been doing a lot of procrastination during the holiday season and the insurrection season and all that. And I did finish up a couple of modules, which I would like to show you at some point. But right now, what I want to show you is what I'm working on now, which is a new module for my synthesizer in progress, Cosmodrome. This is the Music from Outer Space voltage controlled oscillator. And before soldering it up, I had a few questions, concerns, ideas that I wanted to look into. So I thought I'd build it on a breadboard first. That's what I'm going to show you right now. Okay, so this is it. This complicated thing here, and this is an old school ramp core voltage controlled oscillator. There's no specialized synth chip. There's just op amps, discrete components. And okay, one thing to look at is this thing right down here. Don't know how you can see it. I'm blocking the light, aren't I? There we go. So that is something that you find in most of these kinds of oscillators. This is a matched transistor pair. It's two transistors that are very similar in their characteristics, and they're in thermal contact with each other. You could just sit down with a bag of 2N3904s and test a bunch of them until you find two that are matching, and then you glue them together, and that'll more or less work if you do it right. It's certainly the cheapest way to do it, but Ray Wilson, who designed this thing, designed it to use a part which is the SSM2210, which is two transistors that are fabricated on the same piece of silicon, and then they're packaged up in like an integrated circuit. And he used a through-hole version of that, the dual inline package version. But that part went out of production about a decade or so ago. And there are, if you look around, you can find vendors that still have new old stock 2210s in the DIP format. And they'll be happy to sell them to you if you fork over an obscene amount of money for them. But what Wilson did was on his, where's the circuit board gone? Here it is. What Wilson did was on his circuit board, where he had the footprint for the DIP version, he added inside of that a footprint for a surface mount version of the same part in a SOIC package. The SOIC 2210 or 2212, which is the improved version, and that's what I'm planning on using. So for the breadboard, I wanted to use that part, so I have a little adapter board made, a breakout board that takes the 2210 and breaks the pins out to two pin headers so you can plug them into the solderless breadboard. And that's the first surface mount soldering I've done in about a year, and it's maybe the fifth SOIC package I've ever soldered surface mount. So my technique still kind of sloppy, but it works. So there it is. Another part here, which is kind of unusual, I mean it's usual for this kind of circuit, but unusual generally, is a tempco resistor, which is like a regular resistor except that it has a known and calibrated temperature coefficient, and that along with the matched transistors is what you use to take care of stabilizing the temperature sensitivity of this thing. And I'm going to be using one of those tempco resistors in the build, but not on the breadboard. I'm just using a regular resistor there. There's not a whole lot of point in using the tempco resistor unless it's actually bonded to the matched transistor. So yeah, so let's take a look at this. The first thing I did was I built the core part of the circuit, and it produces a ramp wave, and I plugged it in and turned it on. Let's see, where's the ramp wave? The ramp wave is here. So yeah, you can see it on the scope. It goes from 0 to 2 volts. It's as it's supposed to be. And I didn't make any attempt to calibrate it, but I did check the response to the control voltage, and it's roughly 1 volt per octave, so that's good. I tried the linear frequency modulation control voltage, and it responds to that. Let me see if I can show you that. Get just a 5 volts here, and we'll stick it in there, and helps if we're actually looking at the oscillator. Let me get this in here. Okay, here's the oscillator, and then we add frequency control voltage, and it changes the frequency. It doesn't change it as much as I expected, but maybe that's the design. I'm not sure how much it's supposed to. It's definitely working. Whether it's working at the right scale or not is another question, but it's working. Okay, so that's the core. The core seems to be working. One other thing I did. There is a JFET transistor in there, which Wilson specified a PN4391 JFET, which I don't have any of. So I got out the JFETs that I did have, and I tried all of them. So there was a 2N5457, which is one that Wilson mentioned as a possible substitute, 2N5458, J111, a J112, which again Wilson mentioned that one, and a J113, and they all work in the sense that if you plug any one of them in there, the oscillator oscillates. So that is good. Then I took a closer look at the falling edge of the core ramp output, and it looks different with the different JFETs. So the falling time varies, the amount of time it takes to get from the top to the bottom, which is kind of what I was looking for. It's kind of what I expected might be different from one JFET to another. But also the voltage that it falls to changes, which I wasn't expecting. So the two most extreme were the J113 and the 2N5458. The J112 looked almost identical to the J113. The 2N5457 looks similar to the 2N5458. It's not quite as extreme. J111's kind of in the middle. And just show you a couple screenshots. This is the J113, and you notice the horizontal axis is 2 microseconds per box. And the fall time, it takes about 1.2 microseconds to fall from the peak down to where it falls to, which is, if you blow up the vertical scale, you can see that it drops down to about 20 millivolts. Okay, now here's the 2N5458, and it takes 3.2 milliseconds to fall, so nearly 3 times as long. And what really surprised me is it only gets down to about 230 millivolts. So it's nearly a quarter volt on the integrating capacitor when this thing's done. And that, I don't know, is that significant? It seems kind of bad to me, but on the other hand, maybe it really just amounts to an offset and a scale, and the offset gets trimmed away anyway when you set up the ramp wave output. So it maybe doesn't matter, but certainly there's a difference. And as far as this behavior goes, I think the J113 definitely looks a lot better than the 2N5458. It looks like the best of the bunch. So I think that's the JFET I'm going to use. Whether it really matters or not, I don't know. But unless I stumble across some other reason to prefer one of the others, that's what I'm going to go with. Anyway, that's what you can see on the core of this oscillator. So then I went ahead and completed the rest of the breadboard, which is the circuits that produce the actual different waveforms that you're supposed to be able to get, and they all work. Let's take a quick look at them all. So here we have the ramp wave output. It's going about plus and minus 5 volts. That's where you want it to be. That's good. Here we have the triangle output. That also is looking good. Here we have the sine wave output. And this is, if you look at it closely, it's roughly sine shaped, but it's not a really good sine wave. But I haven't played very much with the various trimmers to try to optimize this shape. I think we can probably do better, but you know, it's what it is. And then finally we have nothing. What's going on here? There we go. There we have it. This is the pulse wave output, and let's see. Yeah, we can vary the pulse width here. Okay, so those are all working, and I tried the oscillator sync input, and I can just show you a screenshot here. This is the controlling oscillator is this pulse wave in blue, and the music from outer space VCO triangle wave is there, and you can see it's synchronizing to the controlling oscillator. That all seems to be fine. Now we get down to the last issue I wanted to look at, and this is where this sledding gets a little rough. Okay, so I'm going to try to explain this as clearly as I can. Hopefully it will make some amount of sense to you. So what I'm concerned with here is the pulse width range on the pulse wave. The pulse wave is created by, there's an op amp that compares the ramp wave to a threshold voltage, which you can set with the pulse width knob up here, and it puts out a low value when it's below the threshold, puts out a high value when it's above the threshold. That gives you a pulse wave, and as you change the threshold, it changes the width of the pulse wave. And there's a resistor, which is R68 in the schematic, that's part of the circuit, and Wilson says that he started with a 10 megohm value for R68. He was using that for a while, and then he tried changing it to 1 megohm, and he decided he liked that better. So I ended up actually trying 4 different resistors, 1 meg, 2 megs, 3 megs, and 10 megs. And let's just take a look at what happens with all of these things. Alright, so what we see here on the screen is, you see in purple is the ramp wave, yellow is the threshold voltage, and in blue you see the resulting pulse wave. And as you turn the knob, the threshold moves up and down, and the pulse width changes. If I turn this thing all the way this direction, the pulse width is the fraction of that distance that's covered by that distance. So we're making that pulse width smaller, and if we make the pulse width, if we run the pulse width as small as we can, eventually it gets to a point where you don't have a wave anymore. You just have a flat line here because the pulse width has gone to 0, and so the pulse wave output of the oscillator has shut off. It's still oscillating. You can see it's still making the ramp wave, but there's no pulse wave output. Okay, which is fine. But now, suppose we go the other direction and make the pulse width larger and larger and larger. And we get down to here. And then the pulse wave shuts off, but it shuts off not when it reaches 100%, but when it reaches whatever that is, which if you go ahead and measure it, it's about 80%. So the pulse width range that we get here is from about 0% to about 80%. And at that point, at 80%, the pulse wave shuts off. Why does it do that? I don't know. That's just how it's behaving. Okay, that's with the 1 meg resistor. If I switch over to the 10 meg resistor, now when I try to go to the smallest pulse width, well, I hit the extreme, I hit the limit of the pot, and we've still got a pulse here. It doesn't shut down before I run to the limit of the pot. And so that is the minimum pulse width we get. And if I try to maximize the pulse width, then I hit the pot limit and we've still got a pulse there, so that's the maximum pulse width I've got. And likewise with a 3 meg resistor, you hit the pot limits before you hit the shutdown point, and with the 2 meg resistor, you're sort of on the hairy edge where the shutdown point and the pot limits are in about the same place. Now if the output shuts down before you reach the pot limit, then obviously that determines what your maximum and minimum pulse widths are going to be. But if it doesn't reach the shutdown point before you reach the pot limit, then the pot limit is going to determine what your maximum and minimum are going to be. And changing this resistor R68 changes the behavior with respect to both of those things, and it changes them sort of in an opposite direction, which makes it kind of hard to get clear what's going on. And as I said, I don't know why it shuts down at a non-zero or non-100% pulse width, but whatever the reason is, it happens, and I don't know a way to make it not happen. But obviously, if the voltage at the end of the pot is not large enough to get you to the shutdown region, if you're being constrained like that by that, well, you could increase the voltages on the ends of the pot to increase the pot limits and get yourself further to the point where you reach the shutdown. So then you're not constrained by the pot limits. But this is where things get messy. So a lot of other VCO designs do this kind of thing, and they use fixed voltage limits at the 2 ends of the pot, which would be easy enough to increase if you had to. But in this design, Wilson designed this to have a couple bits of circuitry that are essentially sampling and holding the extreme values, the maximum and minimum of the ramp wave, and he's using those as the voltages for the pulse width pot. Now, I don't know why Wilson did this in such a complicated way. I presume it's to avoid having pulse width fluctuations if the amplitude of the ramp wave fluctuates. But from what I've seen, the ramp wave amplitude is rock steady if you don't change anything. And if you do change the frequency, I went from 200 hertz to 2000 hertz, and the amplitude changed by about like 1.5%. So that would suggest that if you didn't do it this way, the pulse width might change by, a couple percent, but that hardly seems worth worrying about. So I don't really know what Wilson was worrying about. Maybe I'm overlooking something. I changed it so that instead of having Wilson sample and hold voltages on the 2 ends of the pot, I'm just putting plus and minus 12 volts there, which is way more than you need, but it's easy enough to do, and it shows you what's going on. So using that, even with the 10 meg resistor, I can run it down to the point where it shuts off at the maximum pulse width, and I can run it to the point where it shuts off at the minimum pulse width. So if you look at the 4 resistor values, what you find is that the higher the resistance is, the better you are. With the 1 meg resistor, your pulse width range is 0% to 80%, and with the 10 meg resistor, it's gone up to a range from 0% to 98% pulse width. But if we have Wilson's design, then once R68 goes above about 2 megs, then you reach the pot limits first before the shutdown point, and after that, the maximum width is about 90% and it hardly changes, and the minimum width increases as the resistance increases. So what that means is the optimum value of R68 is about 2 meg, which gives you a range from 0% to 88%. And if you go any lower, the maximum width gets smaller. If you go any higher, the minimum width gets larger. And so that's the best you can do. So what do? Do I use Wilson's design and settle for 0 to 88%? Or do I use the fixed voltage limits and get 0 to 98%, but I lose whatever benefits I'm getting from the from Wilson's sample and hold design? Well, how about a third possibility? So using Wilson's approach, taking those sample and hold voltages, but then amplifying them a little. So I tried doing that. I tried adding an op amp here and a couple resistors that amplify the pot voltages by about 25%. And that, I think what happens there is that means that you're no longer getting exact cancellation of the pulse width fluctuations, or the amplitude fluctuations translated to the pulse width. I don't think you get exact cancellation anymore, but you get some cancellation. It's better than no cancellation at all, and you get the full 0 to 98% pulse width range. It's like when you have 12 volts on both ends. So unless I'm overlooking something, this gives you pretty much the best of both worlds. I think I'm going to try building it that way, adding this little bit onto a small piece of strip board on the side. Anyway, that's what I found on the breadboard. I think now it's time to build it. And I definitely will have another video when I finish this thing to show you how it came out. So stay tuned, hit subscribe, and I'll see you next time on Analog Output.